Hello everyone, I'm Dr. Sajeev Singh. So today I'm going to talk about simulated annealing and its application in molecular structure optimization. So I'm going to give an introduction to the concept of simulated annealing. Then we are going to look at the steps in this algorithm and how they can be implemented in terms of a molecular structure optimization. Then we are going to look at different cooling schedules. We discuss convergence criterion, that the criterion we can use to stop the simulation, and also advantages and disadvantages of this method. So this term annealing comes from metallurgy, where we heat a metal until it melts and then let it cool down very slowly so that it achieves a stable structure. So the secret to achieving this stable structure is that we are giving it at high temperature. When the metal melts, we are giving the metal atoms the freedom to move about so that they will somehow come together in a way that will minimize the energy and form a stable structure, skipping the intermediate energy structures. So when we come to a molecular system, we want to minimize the total energy of the system. And the total energy is composed of kinetic energy and the potential energy. And kinetic energy is related to the temperature of the system. And we usually uh, do not want to change the temperature of the system in order to minimize the energy. So what we are interested in is minimizing the potential energy of the system in order to minimize the total energy of the system. And for a system that has more than two atoms, the energy landscape of the system is usually a very rugged one, like as shown in this diagram, where there are so many local minima and a global minimum. So let's look at each of the individual steps of simulated annealing in terms of molecular optimizations. Now, in the first step, let's have a look at how we calculate the energy, which is the objective function, the potential energy, for non-reactive systems, that is systems where we are not interested about the electronic interactions, where there are no chemical reactions occurring. We calculate the potential energy using force fields like amber, charm, bromose. There are many candidates. And if we are dealing with biological macromolecules like proteins and nucleic acids, one of the most popular candidates is the amber force field. And in the amber force field, we can see there are mathematical terms to calculate the bonding interactions as well as the non-bonding interactions. And if it is a reactive system where we are interested in electronic interactions, we can go for methods like quantum mechanical methods like density functional theory or density functional methods, DFT methods. Even in those situations, we had to select certain candidate structures using the normal simulated annealing as it is done for non-reactive systems. So once we select those candidate structures, we can go for further optimizations using methods like DFT method. And when we are selecting an initial structure, we can either, if it is a very simple structure, we can create it, we can draw it, for example, using a software like Gauss view. Or else, if we are talking about the structure like a protein or DNA molecule, then we can download that kind of a structure by going through the available crystal structures that have been isolated by scientists in platforms like Protein Data Bank. So once we have the initial structure, we can have assign a set of initial velocities for each of the individual atoms by using a Maxwell-Boltzmann velocity distribution that is matching the particular temperature in which we are interested in. So this is the mathematical nature of the Maxwell-Boltzmann distribution. Using a random number generator, we can randomly pick certain velocities that match the given temperature. And then we have to assign an initial high temperature, just like in the case of physical annealing. And we have to carefully select this high temperature so that it is not too high, so that it might destroy the system. For example, if it is a DNA molecule, applying a very high temperature will denature the DNA molecule, and we do not want to do that. Then we go to step number 2, where we are dealing with the uh, positions, like how to calculate forces, accelerations, and then the positions and velocities for successive steps. So the initial forces can be calculated, as we know from physics, by calculating the negative gradient of the force field. Then from Newton's first law, which says force is equal to mass times acceleration, once we have the forces, we can divide the forces by mass to calculate the corresponding acceleration. So once we have the accelerations, forces, initial positions, and initial velocities, using integration methods like Verlet algorithm, velocity Verlet algorithm, leapfrog algorithm, we can calculate the corresponding positions, velocities for subsequent steps. Then in the third step and the fourth step, we calculate the uh, energy for the subsequent step and compare it with the energy value of the current step. And if it is a lower value, we will go ahead and accept that as the that particular transition and move to that step. And then if we are only bothered about going downhill in terms of energy, there is a problem. That is, depending on where we start on the energy surface, there is a risk of we moving into the nearest local minimum. If we are only bothered about minimizing the energy, once we get trapped inside a local minimum, most probably we will not be able to come out of that. But simulated annealing has a clever trick to come out of that kind of local minimum. In this step number 5, we can see that even if the energy of the subsequent step is higher than the current energy, we do not discard that immediately. We still generate a random number between 0 and 1 and compare it with this exponential term given here. And if that value of that exponential term is less than the random number value that we generate, still we go ahead and accept that transition even if the energy is higher than the current value. So we accept energetically unfavorable transitions even if that transition takes us to a high energy value, and this probability of accepting that sort of energetically unfavorable values increases as the temperature of the system increases. So that means at higher temperatures, there is a higher probability of coming out of local minima if our system is trapped inside a local minima. So that is the clever trick that simulated annealing uses to come out of the local minimum, and then it can move towards a global minimum, hopefully. So in step number 7, we can see we can continuously decrease the energy of the system. So we start at a very high value, then we gradually decrease the temperature of the system. And to do that, we have different cooling schedules. We have logarithmic cooling schedule, where at kth step, each kth step, we can see as we are dividing by the natural logarithm of k plus 1, this temperature keeps getting smaller and smaller. Geometric cooling schedule, we have this gamma parameter. We can choose it to have a value between 0 and 1. If it is closer to 0, temperature decreases rapidly. If it is closer to 1, temperature decreases slowly. Exponential cooling schedule, we can adjust the value of alpha to decrease the temperature of the system. In adaptive cooling, we use a parameter that changes with the shape of the energy landscape in order to decrease the temperature of the system. Convergence criterion. So we usually start the simulated annealing at higher temperature, and then we finally come to the room temperature in a molecular system, and in between we generate a number of temperatures, and at each temperature we equilibrate our structure. And finally, after we have equilibrated the structure in the room temperature, the simulation will stop. And uh, so another criterion is if the change in energy, the change in energy for subsequent steps is below a particular threshold value, that also can be taken as a convergence criterion to stop the simulation. So now if we look at advantages and disadvantages of simulated annealing method, simulated annealing is a meta-heuristic algorithm. So meta-heuristic in the sense, now it is used for solving NP-hard problems, and it does not always guarantee the optimum solution. It is going to give us a reasonable solution. So that is one disadvantage, because we are not guaranteed to get an optimum solution. And since we are continuously calculating the objective function, if the objective function is mathematically overly complex, then it might affect the rate of convergence of the algorithm. And also if the user is using a logarithmic pooling schedule, that can also result in slower convergence. And unknowingly, if the user is dealing with the energy landscape that is convex, that means there is only one minimum, there are no like a whole lot of local minima, then using simulated annealing can be an overkill, because in that kind of a simple situation, we can use a simpler method like gradient descent method. The main advantage of this method is that it is very easy to code it up using any programming language. Very quickly we can code this up, so it is easy to implement, and it can very easily skip local minima. And even if our energy landscape has rampant local minima, we can still in general without any problem apply this method. And even though eventually, even though we are not guaranteed to get an optimal solution, most of the time we will get a reasonably good solution at quick time. So thank you very much all of you for paying your attention. That ends my presentation. Thank you very much.